Have you ever picked up a shiny rock and wondered what it was made of? Chances are, you were holding a collection of minerals. So what exactly is a mineral? Think of it like a recipe. To be a true mineral, something has to check off 5 specific boxes. First, it must be naturally occurring. That means it's made by the earth, not in a lab by people in white coats. Second, it has to be inorganic, meaning it was never alive. So things like coal or pearls, which come from living things, aren't technically minerals. They're cool, but they're in a different club. This distinction is super important because it separates the geological world from the biological one, even though they are deeply connected in many ways. Next up, a mineral must be a solid. You can't have a liquid or a gas mineral at standard Earth temperatures and pressures. Ice is a mineral, but water isn't. Isn't that neat? The fourth rule is that a mineral has a definite chemical composition. This is the recipe part I mentioned. For example, the mineral quartz always has the same ingredients, 1 part silicon and 2 parts oxygen, written as SiO2. It might have tiny impurities that change its color, but its core chemical structure remains the same. This predictable chemistry is what gives minerals their unique and reliable properties, which is something engineers like us can really count on. The final and perhaps most fascinating rule is that a mineral must have an ordered internal structure. This sounds complicated, but it just means all the tiny atoms inside are arranged in a repeating, organized pattern. Imagine building with Lego bricks. You don't just throw them in a pile. You connect them in a specific, orderly way to build a castle or a spaceship. Minerals do the same thing with their atoms, and this internal atomic pattern is what forms a crystal. This crystalline structure is the fundamental reason why minerals have specific shapes and predictable behaviors. It's the secret code that defines everything about them, from their strength to how they break. So, to sum it all up, a mineral is a naturally occurring, inorganic solid with a definite chemical composition and an ordered internal structure. It's a mouthful, but each part of that definition is crucial. It's what separates a true mineral like a diamond from something that just looks like one, like a piece of glass. Understanding these 5 points is the first step into the incredible world of mineralogy. It's the foundation for everything else we're going to explore, from identifying different minerals to figuring out how we can use them to build the strong, safe structures that make up our world. Consider the science. Now that we know what a mineral is, how do we tell them apart? We can't just look at a mineral and know its chemical formula. Instead, we act like detectives and use a set of physical properties to identify our suspects. These are clues given to us by the mineral itself. One of the first things you'll notice is color. While it's the easiest property to see, it can also be the most misleading. Some minerals, like sulfur, are almost always yellow, but others, like quartz, can be clear, white, pink, purple, or even black, depending on tiny chemical impurities. So, while color is a good starting point, we need more evidence to make a solid identification. A much more reliable clue is a mineral's streak. This is the color of a mineral in its powdered form. To find it, you scratch the mineral against a piece of unglazed porcelain called a streak plate. Here's the cool part. A mineral's streak color is often different from its main color, and it's much more consistent. For example, the mineral pyrite, also known as fool's gold, has a shiny, brassy yellow color. It looks a lot like real gold, but if you perform a streak test, you'll find that pyrite leaves a greenish-black streak, while real gold leaves a beautiful golden-yellow streak. It's a simple test that can save you from a big mistake. Next, let's talk about luster. Luster is the way a mineral's surface reflects light. It's all about how shiny it is. The main 2 categories are metallic and non-metallic. A mineral with a metallic luster looks like a piece of polished metal, like silver or chrome. Pyrite and galena are great examples. Non-metallic lusters have a much wider variety of descriptions. A mineral might be described as vitreous, glassy, like quartz, resinous, like tree sap, like sphalerite, pearly, like a pearl, like some micas, greasy, looks like it's coated in oil, like halite, or earthy, dull and clay-like, like hematite. Describing luster helps us narrow down the possibilities significantly. Finally, we have hardness, which is one of the most useful identification tools. Hardness is a measure of a mineral's resistance to being scratched. We measure it using the Mohs hardness scale, which ranks 10 common minerals from 1, the softest, to 10, the hardest. Talc is a 1, so soft you can scratch it with your fingernail. Diamond is a 10, the hardest natural substance known. A mineral can scratch any mineral softer than itself. Your fingernail has a hardness of about 2.5, a copper penny is about 3.5, and a steel nail is about 5.5. By testing what scratches what, you can get a very good idea of a mineral's hardness and therefore its identity. When you hit a mineral with a hammer, for science of course, it will break in one of two ways. It will either show cleavage or fracture. This property is directly controlled by that ordered internal structure we talked about. It all comes down to the bonds holding the atoms together. If a mineral has planes of weak atomic bonds within its crystal structure, it will tend to break along those flat, smooth surfaces. This tendency to break along specific planes of weakness is called cleavage. It's like a perfectly sliced piece of bread. The break is clean and predictable. The number of cleavage planes and the angles between them are unique to each mineral. Mica is a fantastic example of perfect cleavage in one direction. You can peel it apart into incredibly thin, flexible sheets. It breaks this way because its atoms are arranged in layers with very weak bonds between them. Halite, which is just table salt, has 3 cleavage planes that meet at 90-degree angles. So, when you break a piece of halite, it shatters into smaller and smaller perfect cubes. Calcite also has 3 cleavage planes, but they meet at angles of about 75 degrees, causing it to break into rhombohedrons, slanted cubes. Recognizing the type of cleavage is a powerful clue for mineral identification. But what happens if a mineral doesn't have any specific planes of weakness? What if all the atomic bonds holding it together are equally strong in every direction? In that case, when you strike the mineral, it will break irregularly. This is called fracture. Instead of clean, flat surfaces, you get rough, uneven, or curved ones. Fracture surfaces can be described in different ways, just like luster. The most famous type is conchoidal fracture, which produces smooth, curved surfaces that look like the inside of a seashell. This is very common in quartz and glass. It happens because the break spreads through the material like a shockwave, without any weak planes to guide it. Other types of fracture include fibrous, which looks like splintered wood, and is common in some asbestos minerals. There is also uneven or irregular fracture, which is just a rough, bumpy surface with no real pattern. This is the most common type of fracture. The way a mineral breaks is a direct result of its atomic arrangement. Cleavage reveals the internal grain of the crystal, showing us exactly where the atomic structure is the weakest. Fracture, on the other hand, tells us that the mineral's internal structure is very tightly and uniformly bonded. So the next time you see a broken rock, look closely. Is it cleavage or fracture? The answer tells you a story about the invisible world of atoms inside. With over 5,000 known minerals, how do geologists keep them all straight? They classify them, just like biologists classify plants and animals. Instead of grouping them by color or hardness, minerals are organized into families based on their chemistry, specifically their anion or anionic group. Remember how minerals have a definite chemical composition? The anion is the negatively charged part of that chemical formula. This method works beautifully because minerals within the same chemical group tend to have similar properties and often form in similar geological environments. It's a much more fundamental and reliable way to sort them out. By far the largest and most important mineral group is the silicates. Their chemical building block is the silicon-oxygen tetrahedron, which looks like a tiny pyramid with 1 silicon atom in the middle and 4 oxygen atoms at the corners. These little pyramids can link together in all sorts of ways, in single chains, double chains, sheets, and complex 3-dimensional frameworks. This versatility is why silicates make up over 90% of the Earth's crust. They are the primary ingredients in most common rocks. We'll talk more about famous silicates like quartz and feldspar in a bit, but just know that if you pick up a random rock, you're almost certainly holding a silicate mineral. Another major group is the carbonates. The building block for this family is the carbonate anion. The most famous member of this group is calcite, which is the main component of limestone and marble. Carbonate minerals are very important because they react with acid. If you drop a weak acid, like vinegar, on a piece of calcite, it will fizz and bubble as it releases carbon dioxide gas. This simple acid test is a fantastic way to identify carbonate minerals. They often form in marine environments from the shells and skeletons of sea creatures, locking away huge amounts of carbon. Other important mineral groups include the oxides, where the anion is simply oxygen. This group includes important metal ores like hematite and magnetite, and corundum, which gives us rubies and sapphires. Then there are the sulfides, which have a sulfur anion bonded with a metal. Pyrite and galena are classic examples. Finally, we have halides, which feature a halogen element like chlorine or fluorine as the anion. Halite, or rock salt, is the most famous halide. By grouping minerals this way, we can better understand their chemical behavior and predict where we might find them. Okay, so let's meet some of the most common minerals you'll encounter as an engineer. The rock-forming minerals. These are really the workhorses of the Earth's crust. First up is quartz, or SiO2. As a silicate mineral with a strong three-dimensional framework structure, quartz is incredibly tough and resistant to weathering. It actually has a hardness of 7 on the Mohs scale, no cleavage, and that classic glassy luster. In engineering, we really love quartz. Its hardness and durability make it a key component of concrete and asphalt. Sand, which is mostly tiny grains of quartz, is fundamental to construction worldwide. It's also used in glassmaking and even in electronics because of its unique piezoelectric properties. Next, we have the feldspar group. Feldspars are the most abundant minerals in the Earth's crust, making up about 60% of it. They are also framework silicates, but their chemistry is a bit more complex, containing aluminum, potassium, sodium, and calcium. The two main types are orthoclase feldspar, which is rich in potassium, and plagioclase feldspar, which ranges from sodium-rich to calcium-rich. They typically have a hardness of 6 and 2 good cleavage planes at nearly 90 degrees. In engineering, feldspars are crushed and used as aggregate in concrete and asphalt. They are also a primary ingredient in making ceramics, from bathroom tiles to high-voltage insulators. Their presence in rock can affect its strength and weathering resistance. Then there is the mica group, famous for its perfect cleavage in one direction, allowing it to be split into thin, flexible sheets. The two most common micas are muscovite, which is a light-colored silvery mica, and biotite, which is a dark brown or black mica. These are sheet silicates, which explains their flaky nature. While not particularly strong on their own, micas are important in geology. In engineering, ground-up mica is used as a filler and extender in paints and plastics. And because it's a good electrical and thermal insulator, thin sheets of mica are used in various electronic components. In a rock mass, however, layers of mica can be planes of weakness, which is a major concern for slope stability and foundation design. Finally, let's not forget about calcite, or Calco3. While it's not a silicate, it's the main mineral in limestone and marble, two hugely important construction materials. Marble is used for decorative stone, and limestone is a key ingredient in cement, the glue that holds concrete together. Calcite is soft, with a hardness of only 3, and it reacts with acid. This chemical reactivity is both a blessing and a curse for engineers. It's great for making cement, but it also means that limestone and marble are susceptible to weathering from acid rain, which can slowly dissolve buildings and statues. So, understanding these key minerals is really essential for selecting the right materials for a job and for predicting how those materials will behave over time. We've mentioned a few times that minerals have an ordered internal structure. The science of studying this beautiful hidden order is called crystallography. It's the study of crystals, how they form, their geometric shapes, and their internal atomic arrangement. Why do we care? Because a mineral's crystal structure controls almost all of its physical properties. Its hardness, its cleavage, its density, and even its optical and electrical properties. By understanding the crystal structure, we can understand why a mineral behaves the way it does. It's like having the architectural blueprints for the building material itself. At the heart of crystallography is the concept of the unit cell. Imagine you have a wallpaper with a repeating pattern of flowers. The unit cell is the smallest, simplest piece of that pattern that you could cut out, and by repeating it over and over again in all directions, recreate the entire wallpaper. Every crystalline solid has a unit cell. It's the fundamental building block of the crystal, containing a specific arrangement of atoms. The size, shape, and contents of this unit cell define the entire crystal. The external shape of a perfectly formed crystal, with its flat faces and sharp angles, is a direct reflection of this internal microscopic order. The idea that the external form of a crystal reflects its internal structure is known as the law of constancy of interfacial angles, or Steno's law. This law, established way back in the 17th century, states that for any given mineral, the angles between corresponding crystal faces are always the same. A quartz crystal might grow to be big or small, long and skinny or short and stout, but the angles between its faces will always be exactly 120 degrees. This consistency is a direct consequence of the fixed, repeating arrangement of its unit cells. It was one of the first major clues that minerals had a hidden internal order. For engineers, this is not just abstract geometry. The crystal structure determines a material's strength. For example, the carbon atoms in diamond are arranged in a very strong interlocking three-dimensional framework, making it the hardest substance known. The carbon atoms in graphite, on the other hand, are arranged in sheets that are weakly bonded together. You can slide them apart easily, which is why graphite is soft and works so well as a pencil lead. Same atoms, different crystal structure, and completely different engineering properties. Understanding crystallography helps us predict and explain these differences, allowing us to choose the best mineral or material for a specific task. When we look at well-formed crystals, one of the first things we notice is their symmetry. They often have balanced geometric shapes that are pleasing to the eye. This external symmetry is a manifestation of their internal atomic order. Crystallographers use specific symmetry elements to describe and classify crystals. These are the geometric operations like rotating, reflecting, or inverting that you can perform on a crystal that leave it looking exactly the same as when you started. Think of it like a snowflake. You can rotate it a certain amount, and it still looks like the same snowflake. There are three main types of symmetry elements to consider. The first is a rotation axis. This is an imaginary line that you can pass through the center of the crystal. When you rotate the crystal around this axis, it will look identical to its starting position more than once during a full 360-degree turn. The number of times it looks the same determines the fold of the axis. For example, a cube has 4 fold rotation axes passing through the center of opposite faces. If you rotate it by 90 degrees, which is 360 divided by 4, it looks the same. It also has 3-fold axes passing through opposite corners and 2-fold axes passing through the midpoints of opposite edges. The second symmetry element is a mirror plane. This is an imaginary flat plane that divides the crystal into 2 halves that are perfect mirror images of each other. If you could place a tiny mirror along this plane, the reflection of one half would perfectly recreate the other half. A perfect cube, for instance, has multiple mirror planes. You can slice it in half horizontally, vertically, or even diagonally, and the 2 resulting pieces will be mirror images. The presence and orientation of these mirror planes are key identifiers for different crystal shapes and systems. They dictate the balance and proportion we see in a crystal's form. The third element is a center of symmetry, also called inversion. A crystal has a center of symmetry if you can draw a line from any point on its surface through the center of the crystal and find an identical point at the same distance on the other side. It's like every face, edge, and corner has an identical twin on the exact opposite side of the crystal. Cubes have a center of symmetry, but a pyramid does not. These 3 elements, rotation axes, mirror planes, and a center of symmetry, are the fundamental tools we use to describe the geometric order of crystals. By identifying which symmetry elements a crystal possesses, we can classify it into one of the major crystal systems. Based on the symmetry elements we just discussed, all of the thousands of known minerals can be classified into one of just 7 crystal systems, sometimes called 6 systems, with hexagonal being a subdivision. Each system is defined by the geometry of its unit cell, specifically the lengths of its 3 axes, labeled A, B, and C, and the angles between them, alpha, beta, and gamma. Think of these axes as the framework of the crystal's room. The shape of the room determines the overall shape of the building. Let's take a quick tour of these systems, from most symmetrical to least. The most symmetrical system is the isometric system, also known as the cubic system. Here, all 3 axes are equal in length, and all the angles between them are 90 degrees. This highly regular framework results in very symmetrical shapes like cubes, octahedrons with 8 faces, and dodecahedrons with 12 faces. Classic examples of isometric minerals include halite or salt, which forms perfect cubes, pyrite, also known as fool's gold, which can form cubes and dodecahedrons, and diamond. These minerals tend to have uniform properties in all directions because their atomic structure is so balanced. Next is the tetragonal system. It's like a stretched out cube. 2 of the axes are equal in length, but the third is either longer or shorter. All the angles are still 90 degrees. This results in shapes like 4-sided prisms and pyramids. A good example of a tetragonal mineral is zircon, which is often used as a gemstone and is important for radiometric dating of rocks. Another is chalcopyrite, an important ore of copper. The difference in axis length means that the physical properties of these minerals can vary, depending on the direction you measure them. The orthorhombic system is like a rectangular box or a brick. All 3 axes are of different lengths, but all the angles are still 90 degrees. This system includes minerals like sulfur and topaz. After this, the angles start to get a bit weird. In the monoclinic system, the 3 axes are unequal in length, and 2 of them meet at 90 degrees, but the third angle is oblique, not 90. This creates tilted shapes. Many common minerals fall into this system, including gypsum, orthoclase feldspar, and the mica minerals. The triclinic system is the least symmetrical of all. None of the axes are equal, and none of the angles are 90 degrees. It's a completely skewed box. Plagioclase feldspar is a prominent triclinic mineral. Finally, the hexagonal and trigonal systems have 3 equal horizontal axes and 1 vertical axis of a different length, leading to 6-sided or 3-sided prisms and pyramids. Quartz, calcite, and beryl, like emerald, belong here. So why should a civil engineer, busy designing bridges and buildings, care about mineral cleavage, crystal systems, and silicon-oxygen tetrahedrons? The answer is simple. Every single construction project on Earth starts with and is built upon the Earth itself. The ground we build on is made of rock, and rock is made of minerals. The materials we use, concrete, steel, asphalt, glass, are all derived from minerals. Understanding mineralogy and crystallography is fundamental to understanding the behavior of these materials, ensuring the safety, longevity, and cost-effectiveness of our projects. Consider building a dam or a tunnel. The strength and stability of the rock mass you are excavating is critically important. Is the rock granite, which is full of strong interlocking crystals of quartz and feldspar? Or is it schist, a metamorphic rock full of aligned mica minerals? Those mica flakes create planes of weakness. If water gets into those planes, or if the tunnel is oriented the wrong way, the rock could fail, leading to a catastrophic collapse. An engineer who understands mineralogy can identify these potential hazards, take rock core samples, and design the project to account for the rock's inherent weaknesses. It's also crucial for selecting construction materials. When you're making concrete, you need aggregate, the sand and gravel that make up the bulk of the mix. What kind of aggregate is best? You want strong, durable minerals that won't react chemically with the cement. Quartz and some feldspars are excellent, but if your aggregate contains certain reactive silicate minerals, they can slowly react with the alkali in the cement paste. This reaction forms a gel that expands over time, causing the concrete to crack and crumble from the inside out. This is a huge problem known as alkali-silica reaction, or ASR, and it can destroy entire structures. Knowing your minerals can prevent this. Even the weathering of building stones is a mineralogy problem. A building faced with marble, which is made of calcite, will slowly dissolve in the acid rain of a polluted city. A building made of granite, full of quartz and feldspar, will last for centuries with little change. Understanding the chemical stability of different minerals allows architects and engineers to choose the right stone for the right environment. From the foundation under a skyscraper to the sand in the mortar and the glass in the windows, minerals are everywhere in civil engineering. A solid grasp of their properties isn't just academic. It's a practical tool for building a safer, more durable world.